Hey guys, welcome, and today we're going to be looking at a problem which is reversing a linked list. Now there are two ways to do this. One is recursively and the other is iteratively. Um, let's jump into the explanation first and then we'll look at the code. So I'll be doing recursive first and then I'll be doing iterative solution for the same thing. So let's get in. For the recursive solution, let me first just draw the problem, and actually even before doing that, let's first look at the problem in Leetcode. So we are given this linked list, and we can see that 1 points to 2, 2 points to 3, 3 to 4, 4 to 5, and what we want is this, where 5 points to 4, to 3, to 2, to 1. Essentially, it's just printing the linked list in a reversed order. One of the edge cases that we have to consider is in case we don't have anything as input. If it's just an empty list, we give back an empty list. So let's hash it out, right? And we're going to start with recursive. Let's first draw the linked list. I have 1, 2, excuse my poor handwriting, 4 and 5. In essence, 5 is basically pointing to none. So the way we want to go ahead with this in recursive way would be to recursively go through each of these nodes, right? Go through each of these nodes. And once I have reached the last node, I know that there is nothing else beyond this because the pointer of this node points to none. So reverse of 5 is basically just the same, right? So this remains as it is. Now, when I go back to the calling stack here, what I want to do is make 5 point to 4 and 4 point to none. So I get rid of this pointer. So right now I have 1 pointing to 2, 2 pointing to 3, 3 pointing to 4, 4 points to none, and I have 5 which points to 4. So right now I have 5 pointing to 4 and 1, 2 and 3, which, let me just say, L1 pointing to 4 as well. Now I go recursively on to the top of the stack and I do the same thing, right? I make 4 point to 3, I get rid of this and I point 3 to none. So after this, at this point, I have 5 pointing to 4, 4 pointing to 3, 3 pointing to none, and 1 points to 2 and 2 points to 3 at this point. So as you can see, as I keep going up my stack, I persist this reversed linked list and I flip the pointer. So 2 will not point to 3, in fact 3 will point to 2 and 2 will now point to none. And finally, when I move to the top of my stack, I will do the same thing where 2 points to 1 and 1 points to none. And in the end, I'll have 5 that points to 4, which points to 3, which points to 2, oops, to 1, and finally 1 points to none. If it's still not clear, when we get into the code, this will become even more clear. Now let's take a look at the time complexity and the space complexity of these of this solution, right? Time complexity, O of n. Why? Because I go through each of these nodes one time. Hence, my time complexity is O of n. What's my space complexity? O of n again, because these are recursive calls, which means they are in a stack. That's the call stack, right? When I recursively keep calling the next node, essentially what's happening is at my topmost stack I have node 1, which then calls node 2 recursively, then node 2 calls 3, calls 4, and so on and so forth, right? So each of these is my stack, and I will have as many stacks as the number of elements in my linked list. Hence, my space complexity is going to be O of n. Now, let's jump into the code. Here is reverse list. So, as I had explained, let's first start with our base case. And what's our base case going to be? If not node. That is, if I reach the end of my node where the last node points to none, and now I am recursively I have called none, I will return none. Oops. Sorry, forgot to return. Now, if my it's not now, it's head. Sorry, okay. Now, if I'm at my last node, then I'll return the last node, right? Because if I'm pointing at 5, if you can see in the diagram on the left here, 5 points to nothing. So when I have recursively reached 5, which doesn't point to any other element, I will return that head itself. If not head dot next, that is if I have reached the last node, I return head. Now let me create a variable called reverse, and what I have here is where I make recursive calls to the same function. Head dot next. So I keep going, and once I receive my reversed list, I point head dot next, which is the next element's head points to the current head, and head dot next becomes none, and I return reverse, and that's it. So if I run my code, it should work, and if I submit, it should get accepted. Yeah, 20.4 MB of memory, 89 milliseconds. This is a pretty good solution. Now let's look at the iterative approach. Okay. For the iterative approach, I'm going to draw the linked list again. 1 points to 2, points to 3, points to 4, points to 5. right? Now let's say our current head, let's call it current, I'll represent it by C, is pointing at the first node in the linked list. And let's initialize another pointer previous, which is pointing to none. If I reverse the linked list, that is, if I flip these arrows, what will 1 point to? None, because right now 5 is pointing to none. If I flip these arrows, 1 should point to none, right? Which is exactly what our previous is. So what we do is we point the current to the previous. We reverse, which is essentially reversing the arrow. So we point current to previous, and then we move current to the next node. So now my current goes here and my previous comes here. At this point, when I have moved my current and previous, I have 1 pointing to none, and this is taken off because 1 is now pointing to none, and now I have 2 pointing to 3, 3 pointing to 4, 4 pointing to 5, and 1 pointing to none. Now I point at this point, I point 2 to 1, essentially getting rid of this, and now I move my current to the next position and my previous to where the current was. And as you would have now gotten the hang of it, I keep doing this until when? When do I say that, okay, I need to stop now? When my current goes all the way to the last node. When my current goes all the way to the last node, I know that I have nowhere else to go, and this is where I stop my execution, which is where the iterative loop ends. Now, what's the time complexity of this solution? It's going to be O of n because I travel through each of these nodes once. So the time complexity is O of n. And what's the space complexity? It's going to be constant because I am not using any extra space. The only thing I'm doing is initializing a pointer p that points to none. But other than that, even if I have a linked list of size, let's say this keeps going all the way to maybe like 1000, I do not occupy 1000 memory addresses. I only initialize one pointer, which is p, which points to none. So no matter what the length of my input is, I will always have just this one pointer that I initialize at the beginning, which keeps changing as I progress through the linked list. So regardless of the input, my space complexity does not change. It's always constant. I do not occupy any extra memory as a function of input. And now, having said that, let's write the same problem but using iterative approach. So I have my previous pointing to none and my current at head. So as we discussed, I keep going through the linked list until I am at my last node. So while current, and what do I do? Now if you look at the solutioning, I have to make sure that before I get rid of this pointer, I need to know where 1 originally points to, which is 2. So I need to store this in a temp variable so that when I get rid of this pointer, I don't lose the next element. So what I do is initialize temp, which will be current.next, and current.next will point to previous. Once I have pointed current.next to previous, I now move my pointers. So current becomes or previous becomes current, and current becomes temp. And what do I return? I return previous, because when I'm at the end of my loop, previous would essentially have the entire reversed list. So if I run the code, it should work, and if I submit it, you can see that it has run, and if you look at the memory, it is lesser than the one that we ran before, which was the recursive approach. So the recursive approach occupies 20.4 MB, whereas the iterative approach occupies only 15.5 MB. So this is a much more elegant solution. And with that, we come to the end of this video. I hope you enjoyed it. Please let me know if there are any suggestions, and I'll see you in the next video. Thank you.